So, good morning, everybody. This is part of our D-Day event, and we will have a few talks this morning given by the students of the 27th cycle of our PhD course, and their presentations will cover a number of fields of the ICT area. We will make a slight change in the planned schedule for this morning. The fourth speaker actually will be the first one. Mr. Konstantin Kozmak will give the first talk.
Good day, everyone. My name is Konstantin Kozmak, and I'm working with Professor Luca Pasquale. And today I would like to tell you a few words about my 3-year activity, which has actually got 3 different directions. One of it is related to my previous laboratory in Russia, which is related to ferromagnetic and ferromagnetic B layers. Another one is related to a laboratory here in Modena, where I am now, and it is actually connected to molecular electronics. And my main activity, as you can see here, is related to fast ion-ionic conduction in epitaxial fluoride non-ionic materials. And this activity was completely new for all our group. As in Russia, in here we have started from the beginning, and why we started, why it's an interesting topic, I'll try to tell you now. So why ionic materials or solid ionic conductors are important. First of all, I'd like to tell you why liquid electrolytes are not so good. So here, as you can see, a cell phone which exploded, and liquid electrolytes are not stable, they are dangerous. If something happens with the battery, it can explode, cause leakage, ignition, or some other bad stuff. If you've got a car with liquid electrolyte batteries and sort of collision, it can also cause ignition, explosion, or whatever. If you substitute liquid electrolytes with solid electrolytes, it can give you, it can solve these problems, but for example, as you can see here, there are some examples of using of solid electrolytes nowadays, but we can't apply it to overall industry applications because there is quite a low value of ionic conductivity, so we can't use them without heating. How we can enhance ionic conductivity? There are actually a few ways. The most straight way to enhance of the conductivity is to simply search new materials. Look for it, but it's actually quite a large topic. A lot of people are doing it, and it's quite hard to compete with a huge industry in this field. Another possibility is to modify ionic conductor structure. So if we create a sort of Gettier structure, multi-layer, or solid compound, you mix different solid electrolytes together, or induce several defects with temperature or some radiation. You can create, as you can see on the right part, enhance of conductivity. Here is presented a multi-layer of calcium fluoride, barium fluoride, and as you can see, there are with increase of the number of layers, there are several orders of magnitude enhance of ionic conductivity, which is actually good, and we've made sort of the same experiment, but with different fluorides. Why the fluorides were chosen? Because they are very good for molecular beam epitaxy. We can create really plain, uniform layers, and moreover, strontium fluoride and lanthanum fluoride have been already studied before, and they already showed enhance of ionic conductivity in solid compounds. So we created a Gettier structure, 10 layers, 20, strontium fluoride, lanthanum fluoride, and as you can see here, it provides an enhance of ionic conductivity, so it was a good preliminary result. And how we create these sort of structures with molecular beam epitaxy. So here is the chamber of growth in St. Petersburg, and how it's work. You put the very pure material in a fusion cell, you heat it, and the material evaporates on top of the substrate in the middle of the chamber, and then you can analyze the structure with different techniques, such as diffraction or atomic force microscopy. And here, for example, there are several structures of the big series of our samples grown at different temperatures, 400, 480, 550, and as you can see, small islands grows bigger, so they coalesce at higher temperature, and I want to point out moreover that through diffraction, it can be seen that we've got oriented growth. So it's not just a polycrystal on the surface. So they are very, have got good crystal quality. And after series of preliminary growth, we were able to obtain really planar structure of lanthanum fluoride with, here you can see monoatomic steps of lanthanum fluoride. And of course, there were several defects as voids, screw defects, or linear defects. But we've already understand how lanthanum fluoride grow on silicon and understand the crystal structure of the lattice of lanthanum fluoride on top of silicon, which is quite useful for future studies of these layers. To understand the chemical composition of the layer, we've used X-ray photoelectron spectroscopy, and in a few words, you can understand that it's through if you got a source of light and illuminate the substrate with it, you can excite electrons, and by looking on the electron spectra, so you analyze energy of electrons with special analyzer, which gives you sort of the fingerprint of your material. And as you can see here, it's a fingerprint of lanthanum fluoride, which where it is important binding energy of the peaks, and actually intensity of the peaks are presented here is also important. So if someone, for example, with a sheet of paper knocks on the door of your office and asks, "Che cosa è questo?" you can easily reply, "Lantanio fluoruro." So, but if you, there is a small drawback of this technique. You can study only the surface of the material. So to take some information from the bulk of the material, you have to dig sort of the hole. So you have to do sputtering. Sputtering is the technique where the accelerated argon ions are collided with the surface, and through the collision, you can take away part of the material. So through this technique, we've done a layer-by-layer analysis of our structures, and as you can see, at the beginning, you've got lanthanum fluoride, so 20% of fluorine, no, lanthanum, and 60% of fluorine, but with depths, you can see that oxygen appears. Where does it come from? What is it? Lanthanum oxofluoride, it's already a different material. It got different conductivity properties. It was quite a question, and to reply on this question, another technique, state-of-art technique, high-energy photoelectron spectroscopy at synchrotron was used. Using this technique, you are actually able to register buried interface. So it allows to create high-energy electrons. So you can register, for example, signal from silicon, which is under 5 nanometers of lanthanum fluoride. So here you can see silicon, signal from silicon interface, and actually this significates that interface is clean, no oxygen or no reaction with lanthanum fluoride. And on the left side, it's a lanthanum fluoride peak, which points us on good quality of the sample and no oxygen again. So we've prepared good samples. We've done no errors, which was a good result. But still doesn't give us an answer where does oxygen come from. So we've made irradiation experiments. And here, as you can see, with time, the new feature appears on the right side of the spectra. And this feature actually is related to free lanthanum bonds, so fluorine vacancies. So, there were done 2 experiments, normal and grazing, and experiment at grazing incidence is more surface sensitive, and you can see that the picture is higher, which is related that these changes are on the surface and not in the bulk. So it's like light-induced changes. To proceed, we've done the same experiment with sputtering to understand what's it changing. So 10 minutes of sputtering, and it's actually induced huge changes on our structure. So at first, it's the red curve here. It's clean lanthanum fluoride, but after only 8 minutes of irradiation, we've got huge peak, vacancy peak here, and it's actually already related to lanthanum metal. So we've got completely different surface, which is lanthanum metallic cluster, and as you can see on the right, it's more or less the same process with irradiation with time, but another part of the spectra, valence band, and here you can see that at the beginning it was clean lanthanum fluoride, red curve, but after sputtering, there are metallic features here, here, and here, and after 30 minutes and 500 minutes, it's oxidized, so you've got oxygen features. Understanding of where does oxygen come from can be shown from these 2 pictures. Here you can see huge drop of fluorine. In first 30 minutes, you've got drop of the intensity. You lost 2/3 of your fluorine on the surface. And on the right, you can see small step-by-step increase of oxygen, which points you on oxidation from residual gases. So you have got vacuum in the chamber at 10 - 9 millibar, and still you've got oxidation from residual gases, which was quite surprising. We didn't expect it, but the result is the result, and it's like this. Temperature changes shows us more or less the same picture. So if you heat, we've got change of the surface of our structures, and the same low binding energy shoulder, which shows us irreversible oxidation of the surface. Now I want to tell a few words about the most interesting part of my work, which is multilayers. So multilayers were studied with following geometry. So lanthanum fluoride was under strontium fluoride, and this was repeated 5 times. So it's 10 layers of different material, and here it's presented the signal from buried layer, buried lanthanum fluoride, and as you can see, new feature C appeared from the beginning. So here green curve presents a monolayer structure, and red one is a first spectrum from the multilayer structure. So we've got special interface changes which promote creation of fluorine vacancies in the interface. As you can see below here on the slide, it's transmission electron microscopy image, and you can see that this is lanthanum fluoride layer, and its borders are sharp, and we've got good epitaxial quality of our layers. On the next slide, we've tried to analyze the quantity of the vacancies in the interface, and through the area of these peaks. A peak is related to fluorine vacancies, and lanthanum 5P blue peaks are related to overall quantity of lanthanum. And through this relation, we were able to understand that we've got about 12 times more vacancies in the interface, which is significant, and it was actually proved with conductivity results, which are presented here on the slide, which shows 1 order of magnitude increase of conductivity in the same structure of the in the layers of the same structure. At the end, I want to say that through these years, we were able to understand how ionic conductors, fluoride ionic conductors grow and how they change under different irradiation. They are actually prone to irradiation changes, temperature changes, and actually we were also able to show that these irradiation changes, by controlling irradiation or structure changes, we are able to induce changes on the conductivity of multi-layers, which is good result, I think. And then my other activities and publications. Thank you for your attention. If you got any questions.
Thanks a lot for your talk. Any question?
I have just a question, but I was talking with Luca about the possibility to construct the material and not just only to simulate them. So my question is, which part of your time is devoted to the experiment in real material constructing and reusing, and which part of your time is related with the simulation code, code writing and so on? Just a curiosity, because I'm absolutely in the area, in another area, very more virtual than this one.
Actually, it's quite easy, not easy, it's to create an experiment and reliable experiment. It's a complicated task, but it can take 1 week or 2 weeks, and after this you've got plenty of time. You should put plenty of time on the analysis of the data to understand through the data what is it, what the data is related to, or because it's not clear. These materials were not studied previously as literature. As I said, we've started from the beginning and we didn't know what is it, what's the material, how it behaves under different changes. And as you see that ionic conductors are mobile, they change under time, so it's most of the time was analysis in my mind. Thank you.
Okay, so most of the work was done, for instance, in MATLAB, analyzing data or something like that. So thanks again for your talk. And now we go back to the natural order of the list, and so the next speaker will be Mr. Marco Manfredi.
Okay, good morning, everybody. I am Marco Manfredi, and the title of my presentation is Segmentation Through Recognition and Return. And I'm going to present 3 works that I've done in these years of PhD. What can we understand from this image? Actually, a lot of things. For example, the number of objects, their location, the pose or the parts of which they are composed, the interaction between them. But this presentation focuses on two of these problems. The first is recognition, so understanding the type of the object. And the second is segmentation, so find the outline, so the border of an object. Recognition is actually very difficult. These are all samples of the human class, but as you can see, here there is no face, for example, and this is moving. And segmentation, given, for example, these images, is even more complicated, because this is the expected output of a binary segmentation algorithm. Segmentation can be done in constrained environments. These are examples taken from our work in machine vision application, where we have collaborated with a fashion company. We have a lot of constraints here. For example, there's one object at a time, the background is simple, and segmentation here can be achieved with 100% quality. But this presentation is about less constrained environment. I will talk first about recognition, then how to use recognition for segmentation, so class-specific object segmentation. And then the last work is about class-independent object segmentation, so we are not going to use the class of the object to segment it. At the end, I will draw some conclusion. This is the classic pipeline of object recognition has been the pipeline for 10 years. We have local feature extraction, that is the extraction of small region edges and information. An encoding step, that is transforming this information into a more suitable space. A pooling step, that is how to summarize all the information I have from an image. And the classification step, that gives us a machine learning tool to understand, to find the class of an object. We will not focus on the first and the last step. There are a variety of choices here, and the SIFT are chosen by us because are the most used and allows us to compare with state-of-the-art works. And for classification, we just used a standard tool, an SVM tool, linear in this case. This is the classic approach. We have a training set. We extract some knowledge from these images, like knowledge of, let's say, image statistics. And given an unseen image, we can describe it using its content, of course, but also all the information I have understood from the training set. This is just a description of the image. We want to avoid the use of other data, except from an image. And from this reason, we have proposed the Gaussian of local descriptors, named gold, to describe an image. That is as follows. We have a region to describe. We extract densely the local features, here SIFT. And we just compute the mean and the covariance matrix of the local features in this region and use the concatenation of mean and covariance matrix as the descriptor of the region. Thus, we obtain a multivariate Gaussian. The dimensionality of the mean is the dimensionality of the SIFT descriptor, that is 128. And after the concatenation with the covariance matrix, that is symmetric, so we just take half of it, the total dimensions of the descriptor is 8,384. We use the spatial pyramid representation, that is, we don't just describe the entire image, but we divide it into 4 regions and into 3 horizontal slices. This is to capture local parts of the image, because description of the entire image only is not, does not capture the locality of objects. And the final descriptor of the image is the concatenation of the 8 different descriptors of the regions. This is the final dimensionality. It's quite high, but will allow us to use a linear classifier. This is our proposal. We don't weight all the all the local features in a region equally, but we give more weight to the local features that are in the center of the region. And each descriptor, for example, the descriptor that is here, is weighted both for the first region, for the second region, third and fourth. So it's a bilinear interpolation. These are some results on the Caltech 101 object recognition dataset. It's compared to work of the last 5-6 years. And okay, as we can see, there's 2 different tests with a number of training examples. But our performance are definitely on par with state of the art. So differently from other approaches, we have a descriptor that does not depend on the data set on which the image belongs. It's really simple to implement because it's just a multivariate Gaussian. And as we saw, it's really effective in describing small regions. So it takes really advantage of the spatial pyramid representation. With this descriptor, we participated to ImageClef 2013. It is an image annotation competition, very big, with 250,000 images for training. And we obtained the first mean average precision. We ranked first in the mean average precision in this competition. So we have talked about object recognition, but how to use it for segmentation. So let's say that we know the class of an object in an image, for example, the horse here. The expected output of segmentation, of binary segmentation, is the to have a binary mask of foreground and background. This approach, and also the last I'm going to talk about, is based on GraphCut. That represents an image. Let's say that this plane is an image, where each node is a pixel, and each pixel is connected with neighbors, with what are called binary edges. And each pixel is also connected to 2 virtual nodes that are the foreground and the background, that express the 2 labels that we have. These edges are called the unary edges. The GraphCut finds a minimum cut through this graph that divides the image in 2, and finds the minimum of this energy. This energy reflects the edges that we have seen. There's a unary term, a binary term, and a smoothing parameter that just weights the importance of the 2. If we know the class of an object, we can say, okay, we can build a model of that class, for example, horses, and the unary term will encode the cost of assigning a pixel to the model, here, and the binary term, it's just it's weighted using contrast information. So if 2 pixels are very different color, are of the very different color, they are likely to be disconnected. Just the parameter lambda weights the 2. The literature in the last 10 years has focused on this unary term, so how to construct a reliable model, an effective model for modeling objects. So we have Gaussian mixture models in 2004, the use of texture, the use of shape priors, structural learning for learning the unary term. But here we focus on the binary term and say, can we do better than just using contrast information? Here we propose to learn the binary term and as a binary classification problem. So we just want to know if 2 neighboring nodes are going to be disconnected or not. This is the main approach. We have a training sample with the ground truth mask and the superpixel segmentation. Superpixels are just regions of homogeneous pixels. And here are represented in a smaller scale, very high scale. We just use like 800 or 1,000 of these regions. And given here, we have superpixels of the same label, so inside the horse or inside the background, and superpixels of different labels that lies on the border between the main object and the background. These are the samples of our learning scheme. So we have positive samples and negative samples. The goal is, in testing, we have a graph of these regions. We want to predict the weight of the edges so as the superpixel that lies on the border of the objects give very low weight, and the superpixels that are inside the object or inside the background have a very high, strong connection between them. To describe a pair of superpixels, we use location information, color, and shift distribution, and an information of the edge between the two, so the border between the two. The classifier is just a support vector machine using an RBF kernel. These are some results. All the results I'm going to present are obtained with the same unary model, so it's not changed. This is the approach without superpixel, but using a standard binary term, contrast-based binary term, and achieves this 74.7 of segmentation accuracy. Then, this is our method. We start with very simple features, so only location information of superpixels, and this is the result, so it's even worse than the case without our learned binary term. And then we keep adding features, so the border information, the shift information, the color information, and at the end, with the complete representation, we have a very high segmentation accuracy. And this is the classification accuracy of superpixels. So we see that superpixel pair are classified in a very good way, and this reflects the segmentation accuracy. If we had a perfect classification, so all the pairs of superpixel would have been classified correctly, this would have been the results. It's just an upper bound. These are results on the Weismann-Osis dataset when we compare to another method that uses a similar unary term and the GraphCut as a baseline. Okay. Let's move to class-independent segmentation. So we want to see if not knowing the class of the object to be segmented is good enough to segment it. Our main idea is simple but effective. The one segmentation model cannot be optimal for all objects. So we need some flexible algorithm that can adapt to different objects. This is an example of a dataset. We have very big objects, very small objects, objects with cluttered background, incomplete objects, or objects with very low contrast with respect to the background. For this reason, we propose a method that is based on a central point, central superpixel, and a bounding box. So these are given. And the algorithm uses color, texture, spatial information in the form of geodesic distance, a shape prior, and the ability of refine the segmentation at pixel level, because here we are working on superpixels. This is a representation of this information for this object. So we have the bounding box, we have a shape prior computed using similar objects, we have color information with respect to the central superpixel and the background. We have the texture information, and here, this is the geodesic, that is a spatial information that tells us, for example, the distance with respect to the outer border of the bounding box. Given a group of objects, we can say, okay, we want to learn if a superpixel is on the foreground or on the background, so if it is class 1 or 0. And it's a binary classification again. And the flexibility is given because we can weight this feature given with different values. So we can give a lot of importance to this or this, depending on what is better for classification. So we just took a very common dataset, a very good dataset, Pascal VOC 2012, learned a binary classification using the random forest, and these are the weights that come. So this is the importance of each feature. These are the 7 features I showed above: color, texture, geodesic, and shape. Here we can see that the shape is not really important, because if we compute a shape prior of all objects together, the shape prior is just a Gaussian that tells us that the object is in the center. And then here we have the foreground information, this and this, is not really important because the size of the central point, the central superpixel, is almost irrelevant with respect to the size of the entire object. We need to specialize this model. We obtain one model for all objects, but we want to obtain more specialized objects, and this is our main proposal. It is to split the objects in two, recursively, using a visual feature, and compute a model here, a segmentation model here, that will be more accurate for these objects than the model, the generic model. But we can split on a lot of features, for example, size, shape, color contrast. And to choose the best feature on each split, we just use the cross-validation to choose the one that gives the best performance in segmentation. This is an example of a tree. This is less than half of it. Here we have all the images, so all the objects, 3,000. These are splitted using shape, and then again, size, shape. This is, shape is used a lot here, convexity, and color. And each of these splits computes a more specialized model that thus must give us an accuracy gain. And if we use the model in the root node, we have a performance of 55. If we go through the leaves, we obtain a performance of 64 almost, with a gain of more than 8 points, moving from a generic model to a specialized model. We have a tree of what we call the segmentation prototype that is composed of the model and all the objects that are in the group, so the appearance of these objects. At testing time, we can say, okay, we want to choose the best leaf, and the best is the one that is most similar to the current object. So I'm going to use only the models in the leaves. We applied it to segmentation proposal. It's a very hot topic now, and is based on proposing a number of segmentation for an image, potentially overlapped, to cover all the objects in the image. K, so the number of segmentation is usually really large, is in the range of between 500 and 5,000. And these are results. We are still working on this, so this is not published yet, but here we have excellent works that are published in PAMI and ECCV 2014, so very recent work. And we are, this is an example with 4,000 proposals, we are on par with state of the art, and we are going to, I think we are going to beat them, I hope. These are my conclusion. First of all, object recognition is an achievable task now. One reason is that we have a lot of data available. In 10 years, we have the amount of the available data, labeled data, is grown a lot. And recognition can be used for class-specific models for segmentation. But this constrains us to build a model for each category. And if we see the current trend in datasets for computer vision, these are old datasets. These is presented 3 months ago. This is new also. This is the number of categories, and this is the instance per category. So we can see that it's a logarithmic scale. New datasets are composed of tens of thousands of categories and tens of thousands of objects per category. So we need class-independent models because they give us the scalability to tackle these large-scale challenges because they allow us to share segmentation models within different object classes. Thank you.
Thank you. Very good talk. Any question?
I would like just only say that you forgot to mention that the last part of your work is not, has not been done here.
Yeah, the last work, the class-independent segmentation, has been done in collaboration with the University of Amsterdam. And I have been here for 4 months with Professor Arno Smoiler. And yeah, we are currently started writing the paper of this work.
Just a comment. I am wondering how important is the issue of complexity, computational complexity, important in your community? In the sense that when I want to compare to different techniques, I don't show not only the performance, okay, but also the complexity. I mean, assess it in some way. There was no mention of this technical issue in your talk.
Obviously, because it was not a strong point of my algorithm. Because usually in our community, I think you have to reach high numbers first. And the computational complexity, someone else will work on optimizing your code. You don't have, I don't have time to really optimize the code, but yeah, you have to segment an image here is about 100 seconds to propose 4,000 segmentation, just to give an idea of the time required for it. Thank you.
I am from a different community, and the issue of complexity is very important. I mean, if you have something which has to run on a portable device and you have some constraints on the battery consumption, then and the computational power, then the issue of complexity is really important. So thanks again for your talk. So we have the next speaker, and Mr. Nicola Capodiesci.
Thank you. So, good morning everyone. I am PhD candidate Nicola Capodiesci, and I'm here to present something about what I'm working on during my PhD studies. So the title of this presentation is Design and Application of Collective Adaptive System, an approach based on artificial immune systems. My supervisor is Professor Giacomo Cabri. So we are going to talk about two important topics, in my opinion, autonomic computing and artificial immune system. So we start with autonomic computing. The current trend in designing autonomic system is to think of them able to deploy the so-called self-start properties. So we have to think about system able to autonomously repair themselves, both in terms of hardware faults and software faults, so to reschedule their behavior. Why it is important? Because we need systems that are able to be adaptive to unknown and dynamic environments. And from that, here we have all the self-start properties, so self-healing, self-repairing, self-organizing, and such. On the top of these properties, our research group is studying another self-start property that we call self-expression, which basically deals with the possibility, if we have an ensemble, so a set of computational components, to change the way they coordinate during the runtime execution of a possible task. And we will have some example of that later. So there are some challenges. The point is, the concept of autonomic computing is almost starting to get slightly old. It was originally formulated by IBM in 2001, if I remember correctly, yes. And at the beginning, it was thought as a standard maintenance cycles for softwares. But the systems of today are not monolithic softwares or even modular softwares. The system which we have to deal today are distributed complex systems, possibly large and heterogeneous and autonomous. We have to think about largely distributed agent system or anything that can deploy even a small degree of autonomicity, so even a robot or whatever. So we have different concept of being adaptive, different concept of component, and we need adaptivity. Our proposed solution is to take a look at these autonomic computing related challenges using an alternative approach which is based on bio-inspired intelligence. And my approach is based on artificial immune system. Why is that? I think that our biological immune system is is an almost perfect machine. And it's very fascinating because it's composed of millions of independent cells with no centralized control. It's highly scalable, highly complex if we want, and it is composed by several layers, and the most interesting one, at least for me, is the adaptive layer of the artificial immune system, which basically explains why we are able to heal from diseases and pathogens that we have never encountered before. So, first I start examining what is present and established in the literature. So, the very known IBM's MAPEK model for designing control loops in autonomic computing system on one side. On the other side, we have a representation of a variation of something that is very known in artificial immune system related literature, which is an idiotypic network. What you can see now, it's basically something that was proposed by famous immunologist Iron Cohen, and it's called cognitive immune network. So we start by examining these two ways to design system and to think about distributed and autonomic system, and we drew a map of commonalities and similarities in order to have a starting point. We have seen that there are commonalities, there are differences, but we can bridge them using our concept of self-expression. This is important because there are a lot of typically bio-inspired concepts that are usually not sought enough, looked after properly in autonomic computer traditional literature. In particular, really old concepts like exploration and exploitation, but also the possibility to generate new solutions for approaching the same computational problems, starting from simple and non-adaptive strategies. This is something that is present in artificial immune system, but is not that present or is still under investigation in the autonomic computing community. So what we are trying to do is to propose an hybrid framework that takes inspiration from both of the worlds, and it is able to solve basically these open challenges. So we are proposing this framework that has to be used as design guideline for the system engineer. So to allow him or her to kind of like designing almost any kind of distributed system, provided that is composed of distributed independent units. So this is basically just the surface of this fairly complex framework that we came up with. It is composed by two parts, an offline phase and an online dynamics. The online dynamics, the one in the bottom, is executed locally inside each component. Each component is seen as a virtual lymph node, so is able to host a multitude of interconnected virtual antibodies. These antibodies are organized as an idiotypic network, also known as immune network. Therefore, is not only able to bind with foreign antigens, which in our case is represented by the ever-changing dynamic environment, but is also able to create connection with other antibodies inside of the same component. And so they are able, each component, to decide a response for specific external situation according to its previous knowledge and its current concentration of a specific antibody. And an antibody is a complex data structure that we will see in the next slide. In the offline phase, we have basically a pre-experimental phase, but before that, more importantly, we have to define our task in terms of goal, functional and non-functional requirement, and languages for describing the capabilities of our components. That part of the thesis was done in collaboration with some other researchers from the University of Florence and IMT of Lucca, while the latter part is being done in collaboration mainly with the Napier Edinburgh University in Scotland, United Kingdom. So this is basically, we are getting deeper into the dynamics of the framework. So as I said, each component, each robot, each agent is a virtual lymph node that contains a certain number of virtual antibodies, and each interconnected antibodies is a tuple of at least 3 fields. We have a condition field, which basically creates a measure of distance with the perceived external condition. We have an identifier of a collaboration pattern that can be enacted in order to solve a specific task. And we have a last field, which is basically dealing with functional and non-functional requirement. Basically is what I'm doing, the task that I am trying to solve, what are my performance over time, basically. According to the complex functioning of this network, over time, the concentration that characterizes antibodies will change over time, and the concentration of the antibody will suggest to the single element which collaborative effort and which role inside the collaborative effort should be chosen. And we have this equation, which is a slight variation of one of the many models used for modeling idiotypic network. This is the Ishiguro's model. So basically, I've designed this framework. Now, in order to provide some kind of evaluation procedure for my frameworks to see how good is my work, we have to apply it to different case studies, because I promised that I wanted to try to use it in different case studies. So in this talk, in the remaining part of this talk, I will mainly focus on the last 3 cases, because I already focused enough on smart grid in other talks. And so let's start with swarm robotics. Is also something that I presented in the last D-Day. This is a very nice paper that we published at the European Conference of Artificial Life. And it's basically a very simple foraging task in swarm robotics. And all the robots started with a very restricted set of coordination patterns, very unadaptive. And thanks to the mutation operators that are intrinsic of our idiotypic network, we managed to mix and create new way of coordinating, and they obtained fairly good results that I presented last year, but obviously more in-depth discussion of that is present in the paper. Now, I will spend a bit more words about this case study that was published this year at the International Conference on Artificial Life Synthesis and Simulation. This is basically, we have a virtual creator, which is composed by 10 identical and independent units. And each unit should take a decision on how to act in order to have the whole creature to move by avoiding small and simple obstacles, and at the same time avoiding big energy consumption measures. So the elemental novelty of this creature is that instead of most other things that you can see in the current literature, this virtual creator is composed of 10 independent units, so it's not a central brain. So the controller is actually distributed, and it evolves over time using our idiotypic network. This is basically the antibodies. Once again, we can see that the same structure of the framework is repeated in every case studies, basically. Even in this case, this is slightly more complex because we have a dual-layer idiotypic network. So we have a single idiotypic network inside the single component with all the antibodies inside the single component, and an external idiotypic network for basically exchanging information with nearby units of our virtual creators. We have some glance of the results. Obviously, in the paper, you can find all the statistical analysis about that. And basically, what happens is that we evaluated the performance of our virtual snake with the initial coordination pattern in which he started, and we can see that the energy consumption is adjusting over time, but it's fairly low. And as far as the trajectory is concerned, here we have a top view on how our creatures move, and is able to autonomously decide whenever to step back from simple obstacles such as walls of a small arena. The final case studies is something that I'm particularly proud of, because this paper was published at the IEEE Conference on Self-Adaptive Self-Organizing Systems, and it won the Best Paper Award. It's basically applying our framework to a morphogenetic engineering scenario. So I started from the findings of professor called Hiroki Sayama, and he said, okay, let's take a set of moving particles and let's give them the possibility to move following a very known flocking algorithm, the Boyd's rules. And we know that in the flocking algorithm, the particles are moving following some kinetic parameters, such as their tendency of being aligned or to be repulsive and separation and everything. Sayama called all these parameters as recipes. And he said, okay, let's try to create subsets of this initial swarm and assign them different kinetic parameters for all of them. Let's see what happens. This is basically a very nice and simple example of what happens. We have two swarms. These swarms are very attractive and cohesive force. This one is basically the opposite. We can see much more distance between each particles. No, the point is, what happens if we put them together in the same environment? This is what happens. It emerges inner circular structures. And the funny thing is that it's completely robust. I can go there and perturb it, and eventually this structure will recreate itself again. Obviously, this is a simple example, but we can add different set of particles with different kinetic parameters and obtaining very nice, much more nice to see and complex geometric structure. And all of them are robust. So I can go there, apply some disturbances to the environment, they will recreate the structure. Well, with my framework, we were able to provide evolutionary features to that. So we want our swarm to manage to create those kind of shapes by itself. Because now we have, like, Hiroki students have inserted all of this. Well, I want to provide my system the autonomicity that is necessary to define this. So, basically, our initial coordination pattern is a more restricted set of recipes, so set of kinetic parameters. We defined a fitness function that we use for our evolutionary features, which is basically relates of I am a single particle, because even if we have like hundreds and hundreds of particles, it's still the whole framework, the whole dynamic part of the framework is executed locally inside each component. Basically, we are just trying to decide what will be a very good fitness function. And we just said, okay, let's take your own observation radius and just count how many different particles are present inside the radius over the total number of particles. This is basically in few words. So the dynamics follows exactly the same way as we used in the other case studies that are completely different. And on the top of that, we just added a further layer, which is in defining a measure of distance between known recipes and unknown recipes, which is actually a fairly complex one because it's a huge set of parameters. And this is basically what happens. My swarm evolved to create these structures by itself. And it recognized that these structures are new. So they were not present in the small initial set of recipes, so set of kinetic parameters. This is what happens during a single experiment. We start by complete chaos, because at the beginning they have no way to evaluate their performance, so they basically pick a set of kinetic parameters by chance. Then we have the different evolution with 3 different random seeds. And in order to give some results, what we can say is that we started from 17 initial recipes. The system managed, after a certain time, to create 68 new recipes labeled as new, so very different from the other ones, and I showed you some example of those. And 45 of them were erased, because they being labeled as too similar to the one that I know. This is the basis of what is known as novelty-based evolution, which is something fairly new, and I wish to continue to work on this direction, because evolution based on pure fitness function is getting old, and there are much more to add to it. So that basically would be it. I think that the proposed guideline can indeed be applied to a wide variety of scenarios. Obviously, for each scenario, we have a certain degree of not so autonomic effort. Distance measures, mutation operators have to be thought in advance and have to be somehow case-specific. However, when we applied this framework, we got very fine results in all of them. Once again, please read the paper for more in-depth discussion of each case studies. And I think we also addressed some of the concerns in autonomic computing literature. So thank you very much. I'm more than happy to take questions, but I also wanted to tell you that I have really nice videos of all the case studies that you've seen here. So if you are interested to see them, I would be more than happy to show them to you. Thank you very much.
So one of the videos is showing how the swarm of robots is moving, or something like that.
Yes, yes, I have videos about the swarm of robots. I have videos about the virtual creators, and I have videos about the so yes, I do have a video of the simulation platform in which we use our robots. I have videos of the virtual creators, and I have also the video of the swarm chemistry scenario, which is basically a Java program that Hiroki did, and I just took the code because it was open source, and I implemented my framework on the top of it.
May I ask you a question?
Of course.
With reference to the two different model you proposed, which one is more suitable for more complex computational parts? Because most of that part are fantastic when the computation is very small, the reaction time is very fast, and the communication, like in swarm robot. But let's suppose to have more computational needs, for instance, for recognition or for doing something like this in each node. Let's suppose to have a swarm of robots with cameras, so they have to also to process something.
Well, some of the robots that you've seen, they actually do have a camera, but yeah, they mainly recognize colors and stuff like that, so not as nice as we saw before. But well, computationally wise, it's not dependent from the framework, because the framework gives you some designing guidelines. And the complexity of an idiotypic network, it depends on the distance measures, but it usually, well, we don't have like a proper analysis of the computational cost of that, but it's not a big deal, because what it does is extremely limited. It's basically matching distance functions, basically between known situation and what is observing now.
Yeah, but at the same
And
but at the same time, you can have another process working parallelly and at the same time in order to do more difficult computation. So you can use this model just to do matching. This is enough. Yeah. Okay.
basically, the matching and the mutation operators are applied once during a time interval. So each experiment was divided in several time intervals, and at the end of the time interval we'll actually perform an evaluation and therefore mutations and everything. So meanwhile, they can do whatever we want, basically. And the computational complexity is just as complex as the thing that they are doing in that specific moment. But it really depends on the case studies, obviously. So, okay, thank you.
So, thank you very much again. And we start now the fourth talk that will be given by Mr. Fabio Soci.
Okay. Good morning, everybody. So the title of my speech today is Energy Efficient Devices and Circuits. and all the work that I will present today has been done during my PhD studies under the supervision of Professor Alessandro Chini. So, during my activity, I focus especially on two topics. The first one are efficient device, especially the characterization of gallium nitride-based devices. And these devices, as I will show you on the presentation, they have extremely efficient performance in many applications of power electronics. And the second activities I was working on was the energy efficient circuits that especially I work on modeling of switching converters for thermal harvesting applications and also on the design of RF power amplifiers. However, since today I have limited amount of time available for this presentation, I will focus on the first topic, device characterization. That has been also the most important topic I did during my PhD. So this is the outline of my presentation. I will start by giving you an introduction about the device, the gallium nitride HEMT, high electromobility transistors. Then I introduce the issues of charge trapping. And then in the second part, I will start by presenting some of the most relevant results that we have obtained during the characterization of these devices. And in the third part of the presentation, I will just show you an overview of the activity I carry out during the collaboration with the Infineon Technologies. So, gallium nitride is a wide bandgap semiconductor because it has an extremely high bandgap when compared with the traditional semiconductor used in electronics, as you can see on the first row of this slide. And this helped this material to achieve extremely high critical electric fields. So this is a good point for high voltage application because using these materials is quite easy to obtain high breakdown voltages. Moreover, gallium nitride, as you can see here, has also very good electron transportation properties like high saturation velocity and high electron mobility. On the bottom of this slide, you can see the classical AlGaN-GaN HEMT structure, where we have the heterojunction with GaN and aluminum gallium nitride, and at the interface of these two materials, a two-dimensional electron gas is formed. And is formed without the using of dopant, just because of the presence of spontaneous and piezoelectric polarization. And since we don't have the presence of dopant, we have extremely high mobility in this two-dimensional electron gas that is the channel of our device. So for this reason, gallium nitride HEMTs have demonstrated tremendous performance in many applications, power application, especially in RF power application, where they demonstrate high power density and also high operating frequency. So they have been successfully used for power amplifier in communication network, like the new LTE, and also for the realization of the transmitter in a radar transceiver. However, in the last year, many companies have started to develop gallium nitride HEMT for power switching application. This is a very huge market. As you can see here, there are many applications where we can potentially use these devices to improve the efficiency of power conversion. Okay? However, these very promising performances, the gallium nitride has still many open issues, and probably the most addressed is charge trapping. In fact, any crystallographic defect or impurities within the device structures create energy trap level or a trap state within the band gap of the semiconductor, which is characterized by an activation energy. That is the energy difference between the conduction band and the level of the defect. And the problem is that during the device operation, because of the high electric field, electron can be injected in this trap state and once the electrons are there, they are freeze or trapped because they have zero mobility and they cannot participate to the conduction. And they behave like a fixed negative charge, and the result is that they reduce the amount of charge available for the conduction in the two-dimensional electron gas of the device. And the problem is that because of trapping, we have a dynamic degradation of the performance of the device. So in a device with a trapping, if we measure static and we compare the static and the dynamic characteristic of the device, we can observe reduction of the saturation current, increase of the knee voltage, increase of the RDS on of the device, and threshold voltage shift. These are unwanted effects because they degrade the performance of the device and they create instability. However, these degradations are not persistent, but they are recovered after some time at a low voltage state condition. But the time required for the recovery of the device characteristic depends on the emission, the characteristic emission time, tau E, which is dependent on the traps properties like activation energy and capture cross-section, and is also dependent on the temperature of the device. So now let's start with the consideration of the experimental results. I would like to show you this work where we investigate the effect of field plate structure on trapping phenomena. Field plate is a piece of metal that is grown above the silicon nitride passivation. This silicon nitride passivation is an insulating layer grown on top of aluminum gallium nitride to passivate the surface of the device. And as you can see here, we have a piece of metal connected to the gate. So in this case, we have a gate-connected field plate, which is extended over the gain-drain access region. Okay, so the field plate has reduced the peak of the electric field in this area, in the gate-drain access region, and it has many benefits for the reliability and also for the breakdown of the device. However, in this work, we did a comparison of no field plate and field plate devices to see if the field plate has also effect on trapping phenomena. And what we did first was to measure the dynamic and static characteristic of the device. As you can see, in both no field plate and field plate devices, we observe a degradation of the dynamic performance of the device. So the current, when the characteristics are measured dynamically or using short pulses, are lower than that observed in static characterization. And we see that this degradation was not persistent, but was recovered after some while at zero bias. So it's that was a clear indication of the presence of charge trapping. So we start with a characterization of this trapping mechanism, and we use the so-called drain current transient measurements. Where the device is connected in common source configuration with a load resistance and a constant drain voltage, and is driven using a pass generator on the gate. So the first step was to bias the device on saturation regime with a constant VDS voltage, and then a negative gate pulse was applied to switch off the device. And in this condition, the device was off with a high VDS voltage. So during this pulse, trapping was occurring. Then we switch on again the device to see how the device characteristic recover after the trapping. And to see this recover, we monitor the transient occurring on the drain current. What we saw is that after the switch on, the device does not achieve the instantaneous steady state value of the current, but there were many processes like emission, you can see here, and capture process, and both all these signatures are caused by the emission or capture of electron from traps. Using experimental data, we were able to localize and identify two traps, one in the surface of the device, namely T1, and one located in the algan barrier beneath the gate. Unfortunately, today I do not have enough time to show you all the localization procedure, but it's just based on the observation of drain current transient measurement and experimental data interpretation. But we also did verification by numerical simulation of this localization. But I would like to show you the very interesting result we have obtained is that the presence of field plate strongly limit the surface trapping because he reduced the electric field in this area, and so he reduced the amount of electron injected in these traps. So as you can see here, the emission that we observe in case of field plate of the first trap, T1, is strongly reduced in the device with a field plate. On the other hand, the field plate does not have effect on the traps located beneath the gate. Another work that I would like to show you regards the extraction of activation energy. As I told you, each defect has its own activation energy, and the extraction of activation energy is a very important step toward the identification of the defect, because theoretically to each defect should be associated to one value of the activation energy. So by the knowledge of this activation energy, we can understand which is the defect or the impurities involved in charge trapping. So how we measure the activation energy? We perform again drain current transient, but this time we measure the drain current transient at different temperature, as you can see here, and then by deriving the current curves, we obtain the value of the emission time constant at different temperature. For example, at 40 degrees, at 60, and so on. And here you can see the emission time constant at 100 degrees. So using this point, this emission time constant and the temperature, we can draw this Arrhenius plot, and the slope of the Arrhenius plot is the activation energy of the defect. We can also extract from the Arrhenius plot the capture cross-section. So using this procedure, we have a complete characterization of the defect. And however, the problem we found is that the activation energy measurement is affected by the dissipated power, because during the measurement we have the device on, we are measuring the drain current, so the device is on with a non-zero VDS. However, in these devices, since we have extremely high current density, it's easy to obtain very high power densities, as you can see here, even if low VDS voltages are used. And as can be seen in this graph, we have three different Arrhenius plot that depend on the energy, on the dissipated power during the measurement, and we extracted three different values of the activation energy. So from this measurement, I cannot state which is the real activation energy of the defect. However, we develop a technique to do an accurate extraction of the activation energy using the drain current transient, and this technique takes into account the self-heating caused by the dissipated power. So basically, we measure the dissipated power during the measurement, and we estimate the real temperature of the junction of the device. In this way, we were able to correct the point and extract a unique Arrhenius plot even at different dissipated power. So you can see that after the correction, here on the right, we have that the Arrhenius plot extracted at different dissipated power are nicely overlapping, and also we obtain a unique value of the activation energy. So in this way, we are able to do a correct characterization of the traps. So the last result I would like to show you regards the characterization of power devices. As I told you at the start, in the last 3 or 5 years, many companies start to develop power GaN amps for power switching application. However, in power switching application, usually a normally off device is required for safety reason. And the classical amp structure is not suited for normally off operation because the traditional amp is a normally on device. We have a negative threshold voltage. And to obtain normally off configuration, many different approaches have been proposed by the different companies, as you can see here. However, in this work we have a device which has which obtained the normally off operation using gate recess approach. So basically the thickness of the barrier beneath the gate has been reduced to reduce the polarization effect and deplete the two-dimensional electron gas. However, to limit the gate leakage, because the thickness of the barrier here is just a few nanometers, so we have a very high tunneling current, a very thin insulator layer was inserted to limit the gate leakage current. However, we see that using double pass measurement, that is a setup we developed during my PhD, and basically allowed us to measure the dynamic characteristic of the device starting from different bias conditions. We see that effectively the device has a normally off operation. You can see that the threshold is just some hundred of millivolt above 0, but is still normally off device. However, he presented many threshold voltage shifts caused by the changing on the gate bias point. And we demonstrate that these threshold voltage shifts are caused by a distribution of traps within the insulator layer. And these traps can be charged and discharged by changing the gate bias. So when we change the gate bias of the device, we are basically changing the threshold voltage. So this is an unwanted effect, obviously. So we did a characterization, we developed this model that explained all the experimental data and the threshold voltage shift that we observed. And also we implemented another technique called AC transconductance measurement that allowed us to extract the distribution of trap state within the insulator layer. So basically we extract the energy distribution and also the spatial distribution within the insulator layer. So now I would like to show just some slide about the collaboration project we start this year with the Infineon technology. I was there for 10 months working at the discrete power development department in Villach, Austria. And there my activity was especially focused on the installation of a new double pass setup for the dynamic characterization of gallium nitride amp for RF, but also for high voltage and power application. During this activity, I did the installation of the setup and I do all the procedure for the calibration and so on, and then I start to characterize different technologies of these devices. And here I show you an example, a result that we have obtained, and that has been also published in a conference, presented in a conference. As you can see here, we study using the new double pass setup, the RDS-on dispersion issue. So basically what we saw is that the device RDS-on, which is a really important parameter in power application, increases with the drain bias voltage. As you can see here, using 0 bias voltage, we have the static value, the original value of the RDS-on, and then increasing the drain baseline, it starts to increase. However, we found that this, first of all, we did a complete characterization of this effect using double pass, and then we demonstrate that the geometry of the field plate, in particular the length, has a strong effect in limiting RDS-on dispersion. So using long field plate structure, we can limit really the RDS-on dispersion in these devices. Another work I would like to show you is an activity we did on the characterization of short circuit capability that is usually required for power devices. Basically, in this setup, we measure how long the device can sustain a short circuit condition. So we have the device, which is biased as very high VDS, for example, 400 volt, and then it switches on in a short circuit condition and is drawing a lot of current. So we check how long the device can sustain this condition. However, unfortunately, we start using an old setup which was used for the characterization of silicon devices. And when we put a gallium nitride device, since these devices are really, really fast, much faster than silicon ones, we observed many oscillations. And so the measurement was not possible. So I took care of the optimization of the system. I redesigned partially the system, and particularly the gate driver. And after this optimization process I did, the waveforms were very nice, and we were able to measure and characterize the short circuit capability. And we obtained very interesting results. We were able to also explain the failure mechanism of these devices. Unfortunately, all the results we have obtained are confidential, so I cannot present them. So, concluding this presentation, during this presentation I show you the main activity I carry out during my PhD that was related to the characterization of Algan-GaN HEMTs. And as I told you, during my work I realized many setups for the characterization of these devices, and then using these setups, many novel results have been obtained, especially on the characterization of defect and traps. And finally, I had this very nice opportunity to work in the R&D department of such a big company, an important company like Infineon Technologies. So this is the list of my publication, and I finished. Thank you, everybody, for your attention.
Thank you for your presentation. Are you still working at Infineon? I mean, are they planning to offer you a position for?
Yes, I already signed the contract.
So you've already been recruited at Infineon?
I will start on 8th of January.
Just after Christmas holidays. Okay, which is an excellent result, and congratulations for this. Okay, so is there any question? Okay.
It's just a curiosity. Maybe I already asked you previous times. Who provided you the devices, the gallium nitride, and well, the devices that you tested actually?
So I'm not sure that I can answer completely to your question. So we have many projects. The two results I show you, the first two were done on RF devices. They were provided by Silex. They have this department working on gallium nitride and especially on RF application. And the other devices for power application is better to to say. But we work always with companies, and okay. So unfortunately, we don't have the facilities here to develop the device, and but all the products we tested were from industrial companies. So, okay.
Thank you very much again. So the next talk will be given by Francesco Maria Pugliesi.
Okay, thank you very much for the introduction. Okay. Do we have a pointer? I think there was a pointer. Or oh, it's just here. Okay. It's gone? Okay, so, okay. Don't worry about that. It's okay. Oh, thank you very much. Okay, so I'm going to give you an overview of my research activity throughout these 3 years. And again, my name is Francesco Maria Puglisi, and I worked under the supervision of my advisor, Professor Paolo Pavan. And I will try to deliver you a unified understanding of hafnium oxide-based ReRAM operations, modeling, and reliability. So first of all, I would like to highlight the purpose of this work. And in an overall perspective, it was just to attain a compact modeling of these devices, hafnium oxide-based resistive RAMs, based on their physical properties. And actually, the physics of these nano devices is quite complex. So achieving a compact and functional representation of the working mechanism of these devices is not a trivial task, even because we also want to include reliability issues. Now, these devices are really, their industrial exploitation is still hampered mostly by reliability and variability issues. So we really want to understand the physics of these reliability issues and include them in a compact modelization of these devices. So we have to understand the ReRAM operation, understand random telegraph noise and cycling variability, which are the two major concerns for these devices, and we want to clarify their nature and possible relations and put everything together in a single box. So we want to have a unified framework, which is based on physics, but we want them to be very compact and fruitful. So this is the outline of the presentation I will give you. I will introduce these objects, and I will introduce to you a couple of analysis tools I developed, namely a compact model to map the behavior or the operations of these devices, and some analysis tools for the complex noise, the random telegraph noise that we observe is a disturb, as we will see. We will look at it as a resource, as a research resource to understand what's going on in these devices. And then I will show you I would like to show you more, but one big experiment and the results, the most important results we obtained from this experiment, and then I will draw some general conclusions. So, for those of you who are not familiar with these objects, with this hafnium oxide-based resistive random access memory, well, that's an emerging non-volatile memory, a non-charge-based emerging non-volatile memory. Now, it's very simple, actually. We have a layer of HFOX, HFO2, it's basically an oxide layer, sandwiched between two metal electrodes. In this case, we used the titanium nitride. And that's basically it. That's an insulating structure, of course, as is, because we have a metal insulator metal structure. But actually, we can break it down. We can break it down if we apply a voltage ramp, we can break the device down. However, if we control this breakdown by imposing a current compliance, as you see over here, then we are not really destroying this device, but we are kind of building a conductive path, a conductive filament in this structure. And if we are good enough in controlling this breakdown, now this breakdown comes to be reversible. So first of all, with this kind of forming, a so-called electroforming procedure, we can break the device down, we can create a conductive filament, and we determine a low resistive state. However, when I reverse the polarity across the device, I can actually switch this device back to a higher resistive state. Actually, we just locally break the filament, and I can do this on and on, and I can switch the device back and forth from low resistive state to high resistive state and vice versa. So here we have a memory, and we actually have a pretty good memory. It's a good memory because we have low operating currents and voltages, which will pave the way, I hope, in the future for a few femtojoules per bit operation, which is quite a remarkable result for integrated memories. They are very good. I mean, they have satisfactory endurance. They are very fast. They have a high yield on the wafer. Most importantly, they are fully compatible with the actual standard CMOS backend of the line, so we can actually build integrated high-density memory in the same chip that we use to process the information, which is kind of good. It will solve, will speed up the most important bottlenecks of computing machines, which is logic and memory are separated. But of course, it's not only wine and roses. We also have some open issues. most importantly, variability issues, as I told you. The variability and reliability related issues are major concerns for this technology. The device-to-device variability can be quite significant, so different devices are going to behave differently, but also cycling variability. So the same single device from time to time is going to behave differently, which is a kind of writing procedure related source of variability, but also regardless the peculiar resistive state in which we are at a given instant of time, we also have a read disturb. When we try to read the content of the cell, we apply a small constant voltage. We don't have a constant current, but that's the mess we have. It's a very complicated noise. It's called random telegraph noise, because the read current actually randomly fluctuates among discrete levels, and this fluctuation can be extremely wide, so they can cause the failure of the read operation and erratic bit detection. So noise is really, random telegraph noise and cycling variability are really enemies of this kind of technology, but we want to understand what's going on, so we're going to look at this phenomena to try to understand what's going on. So I will give you the details of this compact model I developed. And it took a while to develop the complete model, of course, but it's really based on a simple assumption. So now here you can see the schematic depiction of the device in the pristine as fabricated state. It's insulating structure. Then I told you we can break it down, we control the breakdown, and we end up creating a conductive filament, and we determine the low resistive state of the device. So this is the low resistive state. This is an ohmic-like conductive filament. The charge transport in this regime is ohmic-like. Here we are on a logarithmic scale, but trust me, you have to take my words of it. This is linear, this is ohmic. And when I apply a reversed polarity, DC sweep or pulse, what I can do is actually break this filament here at the bottom end, and I can create a dielectric barrier. So this orange part here is not conductive anymore. Let's say it has mostly insulating properties, and the higher the absolute value of the voltage that I use during the reset process, which is the deeper I go this way, the thicker the dielectric barrier will be. And actually the charge transport here is radically different because it's dominated by some kind of trap-assisted tunneling across this layer, thanks to some traps. They are oxygen vacancies, they are active defects in this structure, and they can carry some currents. Now in this state, in low resistive state, of course when I perform the set procedure, I apply a positive voltage back again, and I can break this barrier again, and I can be again in low resistive state. So in low resistive state, the most important thing is that we have ohmic conduction. We can just represent this filament through this resistance, and of course S is going to be the cross section of the filament, and we can control this with the current compliance. During forming and during set operation, when I have to take care of the device, I don't want to permanently break down the device, I impose a current compliance. The higher the current compliance, the thicker the filaments, the lower the resistance in low resistive states. But when I apply the reset operation and I create this dielectric barrier over here, I have also another piece, another component of my resistance. So I can define generally the resistance of the device, no matter what the resistive state is, as the summation of two components. One component is the remaining part of the conductive filament if we are in HRS, or the whole conductive filament if we are in LRS, and then we have the resistance of this dielectric barrier, which is expected to be exponentially related to the dielectric barrier thickness. And this really completely maps the complex underlying physics, thanks to this K factor here and this temperature factor, which accounts for the temperature dependence of the charge transport across this barrier layer. Then the most important thing about this model is that you don't have to really understand what's written here. The most important thing is that with a very simple model, we can map the electrical response of this device to the physical characteristics of the filament within the structure. So by looking at the IV curve, a very simple experiment, we can extrapolate the cross-section and eventually, when we are in high resistive state, the thickness of the dielectric barrier. So we can relate electrical and physical characteristics. And But I also told you that we are dealing with a read disturb. It's called random telegraph noise, and it looks like this. We apply a constant voltage, a small constant voltage, to read the content of the cell. We don't have a constant current. We have a mess like this. So the current is randomly switching between discrete levels. We don't know how many discrete levels a priori, and that's completely random. Now, in the most simple case, we have a 2 levels fluctuation. It's the simplest case that we can have. And if we have 2 discrete levels, we refer it as 2 levels RTN, and typically, this comes from the literature, this is associated with some kind of trapping and detrapping activity at some defect sites in our device, for example, here in the barrier, but it's just an example. And a 2 levels fluctuation is associated to 1 defect. But we are dealing with multi-level RTN, so we argue that there are multiple traps in the device. Now the question is the following. How can I separate the single trap's contribution, which is, I have this signal, how can I tell how many defects are contributing to the signal, and what are the properties of each 2-level fluctuation associated to each individual defect, which summed up gives back this. So if I want to perform a multi-drop spectroscopy, I have to answer this question, and the answer is actually I have to look at RTN as a superposition of many 2 levels RTN, each of which is associated to an individual defect. And if I want to study this kind of complex signal, this is non-trivial at all. We mutuated an algorithm from the machine learning community guys. It's called the factorial hidden Markov model, and you don't have to know what a Markov process is or what a Markov chain is. It's not important here. It's just that we see the system generating the RTN as a superposition of independent Markov process. Now, you don't have to know that, but this is the output of the system, is the current we are observing over time. So here we have, at the instant of time number 2, we see some current, and the value of the current that we see actually depends on the states of many independent chains. Each chain represents a 2 levels fluctuation. So this is the state of the first chain. It can either be 0 or 1. This can either be 0 or 1. This can either be 0 or 1. We can have up to k chains. So the combination of their states is related to the current that we see. So by modeling the system hidden behind the RTN this way, we are able in doing this. We take a multi-level RTN, this is experimental data, this is the FHMM fitting, and with this technique, the technique itself is saying us, okay, you need 2 traps this time, 2 defects. It's the technique telling us that we need 2 defects to properly characterize the signal, and this signal is actually the superposition of this, defect 1, and this, defect 2. So I can actually characterize the statistical properties, the thickness of the fluctuation, and the typical time spent by the system in each state separately for the 2 defects. This fluctuation here is actually this tiny fluctuation over here. There's 2 different scales. So we can really perform a multi-defect spectroscopy. We can simultaneously study, but independently study different defects, and we can know how many defects we need. Now I would like to show you more, but I have to show you only one macro experiment. And here we go. We take a device, we form it with a given current compliance, and then what we do is to perform 100 full switching cycles. So we set the device, and we have this first part of the IV curve. Then we read the device. We applied a fixed small voltage, 100 millivolts, typical example, and we read the device. We just sample the current over time. Hopefully we see RTN. Then we reset the device under given reset condition, and we read the device in HRS this time again. And we do this back and forth again and again for 100 full switching cycles. So we have IV information for both processes, and then we also have I versus T, potentially RTN information in both resistive states, 100 cycles. And of course, we can repeat this for different current compliance, different devices, different recent condition, different whatever. And first of all, we tried to devise a model for the cycling variability. This is a cycling variability. This is just switching the device in the same condition. These are the conditions, for example, of this particular example. And this is what we get when we look at the distributions. We have a distribution of values of the read current extrapolated from the IV curves. And as we can see, in LRS and in HRS, we have two different behavior. In LRS, we have a normal distribution of the current, and a normal distribution of the current is related to a normal distribution of the effective cross-section. This means that since the set process which drives the device in LRS is stochastic, each time we are going to form a filament which is slightly different in terms of effective cross-section. So that's why we have a normal distribution of the cross-section, which reflects to the normal distribution of the current. But if we look at the current in HRS, then things are different. Here we clearly see not a normal behavior, but a log normal behavior. And a log normal behavior is related to a normal behavior, a normal distribution of the barrier thickness. When we are in HRS, we have a dielectric barrier, and we have fluctuation over cycling of this barrier thickness just because of the intrinsic randomness of the reset process. It involves several atoms and ions. So we expect this distribution to be normal, and as a result, this reflects in a log normal distribution of the current just because the two are exponentially related. So if this varies normally, this is exponentially related to x and is gonna show a log normal distribution. Indeed. And if we exploit the model to relate, I think this is gone, the model to relate the resistances to the physical characteristic, we may end up actually simulating the cycling variability, and that's what we did. So with this model, we can really capture the essence of the cycling variability so that we have a compact model which is variability aware, and we can exploit it to have variability aware circuit simulations. And this is the whole thing about cycle-to-cycle variability. So we successfully included it into the compact model. But remember, we also have to deal with random telegraph noise. And random telegraph noise is just an alteration of the charge transport mechanism. So since we have two different charge transport mechanisms in the two resistive states, I have to separate the two things. So first of all, we're going to devise a model for the HRS RTN. Now, in HRS, I have to recall that we have a dielectric barrier, which is not present in LRS. We have the whole conductive filament. In HRS, we have this dielectric barrier, which is limiting the charge transport. So we are going to look directly at the barrier. This is not the whole device. This is only the barrier. And in the barrier, we have oxygen vacancy defects, which are assisting the current with very, very fast capture and emission processes. Now, it has been assumed in the literature to explain the RTN that for some unidentified reason, this defect may be deactivated, randomly deactivated. So they are driving some current, they get deactivated, they don't carry any current anymore. But then they can get, for some other reason, reactivated and then can join current conduction again. There's plenty of oxygen vacancies driving current into the barrier, but they can get somehow activated and deactivated. The question is how? And this is still unanswered. We will end up having a proposal for that. Now, I should recall that the analysis that we do on noise, we take a trace, we take an RTN trace, and we get to know how many defects we need to describe that experimental data. So with 100 switching cycles for each resistive state, we have 100 RTN trace. For every RTN traces, we can have a given number of traps. We don't know it, but we can plot it for different conditions of the device for 100 switching cycles. So in this graph, we see that most of the times, out of 100 reading operation, we have one trap. Some other times we have 2 or 0 traps. Last time we have 3, 4, and 5 traps. But as you can see, if I move the reset condition, which I have thicker and thicker barrier, this distribution moves. And if I take as a statistical indicator of the complexity of noise, the integral mean of these cards, I have out a number which is referred to 100 switching cycles, and it tells me the average complexity, the statistical complexity of noise. So we're going to use this value as an indicator of the complexity, how complex this noise is. And that's a very intriguing result. If we look at this indicator, the effective number of traps, which is just a statistical indicator of the complexity of the noise, we see that there is a universal relation with the barrier thickness. So the thicker the barrier, no matter what the device structure is, no matter what the reset condition is, no matter what the current compliance is, it's just the barrier thickness. The thicker the barrier, the more is the probability, the statistical probability that I have a larger number of defects, just because the barrier is thicker. And if these defects get activated and deactivated, I have more statistically more complex RTN because of more defects contributing to my RTN signal. And this is really interesting. So this is really depends on the barrier thickness, and that's it. And this picture, activation and deactivation, is confirmed if we look at the statistics. Here we plot the delta I of each defect that we detect in every condition. And as we can see, the average value of this distribution exponentially scales down with the reset voltage, which means, again, thicker barrier, lower general current because the resistance exponentially increase with the barrier thickness, so the current goes down exponentially with the barrier thickness, and also current fluctuation. As you can see, delta I over I, which is the fluctuation over the average value, is always the same, does not depend on the barrier thickness. And of course, because this is completely in line with the activation and deactivation theory, the current step in this theory is actually the average current that the defects drive when it's active. Then it falls to 0. Every defect when it's not active falls to 0. That's why delta I over I seems to be constant in this perspective. So this is really in line with the activation and deactivation theory. And we ended up proposing a model. So how these defects can get activated and deactivated. Now we suggested that there may be an additional defect, we don't know which kind of defect is this, that initially is empty and everything flows smoothly. This oxygen vacancy is carrying some current. But upon a charge capture from this defect, the local electric field induced by the trapped charge can actually modify the field of the oxygen vacancy in such a way that the oxygen vacancy is now not available anymore for charge transport. But however, the initial portrait is restored upon the defect charge emission. So when we capture and we emit charge from this additional defect, we can disturb the property of a closed oxygen vacancy. And actually we recently identified this additional defect with a species naturally present in the device, which is the interstitial neutral oxygen, and we are sending this paper to IRPS, so keep a finger crossed. And another explanation exists. It involves metastable states, so no additional defect. The oxygen vacancy for some reason can go into some metastable states during which it cannot assist the current. They are still unidentified in this structure. And we did the same thing in LRS, and as you can see, we can now modulate LRS not with the reset condition, but with the current compliance. And as we can see, there is the same statistical relation between the reading current and the current fluctuation. Delta I over I is always fixed there, which means the RTN fluctuation statistically follow the read current. And we can see this linear statistical relation here. The average current fluctuation and the average read current are linear, and they follow the current compliance. Higher current compliance, thicker filament, lower resistance, higher reading current in the same condition, thicker current fluctuation. That's the message of this chart. And also, the statistical complexity of noise increases with the barrier thickness, with the cross-section, of course. Larger filament, many defects, higher complexity. So we have a model also for this, and we cannot see the filament as point defects. The filament is really a highly dense cluster of defects, and we have to treat it as a metal, as an ohmic-like piece of conductor. But we have it is surrounded by defects, and the charge trapping and detrapping at these defect sites may induce a kind of screening of the walls of the conductive filament and may cause RTM fluctuation in a very similar way to HRS, but now the defects are located elsewhere. But it seems to us that the defects are exactly the same. Oxygen vacancies and the interstitial oxygen are used to simulate these dynamics, and actually we have this nice matching between lines and symbols, simulations and experiments. So it seems that these models we proposed can really explain the very nature of RTN, and it paves the way to the incorporation of this effects in the compact model. So concluding, we successfully analyzed the behavior of the trap. We developed a compact model which is able to grab the statistic and the dynamic characteristics, and also the cycling variability. Thanks to the IV compact model and the model we developed to analyze RTN RTN combined together, we ended up with an explanation, a possible explanation for this complex phenomena in these devices, and incorporated the whole thing in a unified framework. And I have also to thank, last but not least, Sematech for giving us samples and for a fruitful collaboration throughout all these 3 years. So thank you so much. This is the list of partial list of authors' publications, and that's it.
So thanks for your talk. You have a large number of publications, and they are very focused on a specific topic. So it's a very focused activity.
Well, I actually had to develop also some strategies to. I also have to develop some strategies to analyze this kind of signals. The complex RTN signals that you saw are kind of ubiquitous in nano devices. You have them in ReRAM, you have them in MOSFET. The physical implication may be different, but first of all, I had to try to find a mathematical description which was suitable for this particular situation, and it was not trivial at all. And also I had to develop some models. So yes, this fortunately led us to a big number of publications that were also really acclaimed by other people. So it's a good result from my perspective.
So, thanks again. And now we have the last talk. And the last speaker of this morning is Mr. Marco Natali.
Okay, good morning, everyone. I'm Marco Natali. I'm working at the CNR, at the Institute for Nanostructured Material in particular, for my PhD. And this is the title of my research topic, Integration of Photonic Structures into Field Effect Light Emitting Devices. During my PhD, I dealt mainly with organic optoelectronics and photonics devices, like organic light emitting transistor as a platform for advanced photonics. So we will see in brief the fabrication steps and the modifications we implemented to the heterostructured tri-layer and to the dielectric in order to gain much higher performances in the light emission. Let's start to see the huge multifunctionality of an organic field effect transistor in general. We can design sensors, organic non-volatile memories, organic phototransistor, organic light emitting transistor with different functionalities in respect to inorganic materials, like, for example, the flexibility, the low-cost production, the biocompatibility, for example. Today my talk will be focalized mainly on the organic light emitting transistor. We are driven by different benefits present in the field effect architecture, like the spatial tuning of the emissive region in function of the applied bias that lead to high external quantum efficiency, because we have no metal exciton quenching, no metal photon interaction, and also no exciton polar quenching. Furthermore, the integration potential is very high in this optoelectronic device. Unfortunately, there are several drawbacks, like the narrow emission area, which limits the application, and the poor spectral purity we tried to solve. I show here the optoelectronic devices we used. The first one is an OLED tri-layer heterostructure, where you can see the emitting and transport region decoupled. So we worked on the heterostructure engineering in order to obtain channel-wide illumination. The second one is an OLED NT4N based. It's a single layer device, so we can build up many of them in order to try to integrate a new optoelectronic gate dielectric fabricated by the Politecnico of Milano by pulsed laser deposition instead of the classical, the standard PMMA dielectric layer. Let's see in brief the fabrication steps. We buy the glass covered with a patterned ITO. So we just wash the chip in using an ultrasonic bath 2 times in acetone and 1 time in isopropanol. Then we spin coated the dielectric on top of the gate. Then we anneal it in a vacuum oven. I sublimate the electron transport layer in high vacuum evaporation using the using only one organic material source. This is the host-guest binary system able to create the charge recombination and so the light emission. I use here 2 different crucibles because we create a binary system, so I change, I have 2 different rate deposition for 2 materials in practice. Then the host transport layer, and finally the drain and source electrodes. You can see here a lit linear layer OLED with this geometrical dimension. And here the electrical characterization I executed. You can see here that the mobility are almost identical. Also the threshold for electrons and for holes are in modulus almost equal. It's important to note here that we have an evidence of charge diffusion in the recombination layer. You can see from here, because there is an hysteresis, and also here, there is a little bit of saturation in this point at more or less minus 30 voltage. But you see the current goes down, but the light goes up. So it's a proof of migration of electrons into the recombination layer. So here what I observe under the optical microscope. When I apply an ambipolar polarization, so under the ambipolar regime, the electron and the holes are very balanced. So we obtain the light emission in the center of the channel, and it is very wide. It reaches almost the total length of the channel. Important thing is that there is no light emission under the electrode. Okay, now the questions here were, is there light outcoupling enhancement in ambipolar condition, and at which interface or interfaces does exciton recombination happen? To answer to the first question, we used our homemade setup. It's very easy. We have a rotation stage with a sample holder on top. We use a light chopper to increase the signal-to-noise ratio because it is connected to a lock-in amplifier. And in front of it, there is the photo multiplier tube. Here, the requirements for the optoelectronic device are really stringent. We need device reproducibility, optoelectronic stability, and emission area homogeneity, which is not trivial for organic materials. Let's see here the angular emission profile. We saw that the angular emission profile is invariant. So the light outcoupling is independent on the applied bias. This proves that the effect of the electrodes in our structure, it is not so important. It is not so relevant. There is a slight Lambertian emission overestimation here in this point at more or less minus 70 degree due to total internal reflection, but also the electroluminescence, it is not modulated at different angles. So this demonstrates that there are no optical microcavity perturbation inside, like usually in OLED is present. We did almost some optical electronic simulation. So here we used these two structures to approximate the OLED in the unipolar polarization condition. Because if you remember here the image, in unipolar polarization you have the emission under the electrode. So we use this kind of multi-layer structure with a gold on top. In the case of the ambipolar regime, we don't have the gold on top, so we used this two multi-layer structure. The yellow line is the distribution of excitons we put inside the device, and we saw that this pink shape, this pink curve, it is not present in our results. So we can conclude that there is no metal-induced quenching. And in the other two cases, there is a little bit of superposition here. So in practice, it is not the process. It is not dependent on the single interface, but we think that the recombination process is inside the bulk of the material of the recombination layer. Now, we were also interested in the study of the width of the emission zone. How is the emission zone extended? Well, in OLED 3 layer, we saw 8 micrometer in the center, 70 in the red one, here more or less 50. In modeling approaches on single layer OLED, there are different works in literature that say that the maximum emission zone is 500 nanometer. We saw 3 micrometer wide in this single layer OLED. So in practice, the scenario, it is not so clear. So for that, we implemented a new characterization tool. It is named confocal photoluminescence electromodulation microscopy. And it is very useful because we can observe the recombination zone in operation regime without light emission. The in-plane resolution is more or less 300 nanometers, so we can apply this technique to different devices. Here, I show the result on the NT4N. These results are unpublished, so I cannot go deep in details, but it's clear to see that we can map the real recombination zone as a region of negative quenching in the channel. So in the same setup configuration, you can compare the emission with respect to the recombination zone. Now, let's skip to the other modification we implemented to the device. The photonic crystal gate dielectric into the structure of the OLED. Here, the electrical and morphological requirements are rather stringent. We need high capacitance, ability to sustain high voltage, low gate leakage current, low density of electron traps, and low surface roughness. The surface roughness, it is good in comparison to the standard PMMA. We have a roughness of 3.37 nanometer, and Yeah, it is not bad, but anyway, we decided to put a buffer layer of PMMA on top of it in order to planarize even more the structure. Also, the photonic requirements are not stringent because we need the superimposition between the NT for N photoluminescence and the transmittance of the photonic crystal. Moreover, we need a deep photonic band gap to affect the photoluminescence of the emissive organic material. We used our homemade reflectivity setup to take out these two 3D reflectivity angular map. So you can see there is a good, there is a superposition between the emission of the material and the transmittance. The superposition, it is not so good, but if you want to red shift this transmittance, you obtain a thicker dielectric. So we were scared about the current because, we didn't know the quantity of the current. So we started in this way. Here the electrical characterization, where you can see the locus, curve, N-type and P-type. You can see that the current is much higher in comparison to the standard devices. So we are happy, it's a good result. Also here we took out the saturation transfer curve, P-type and N-type to verify the ambipolarity of this material. But here it's important to note the low gate source leakage current. It's very, very low. So I think the device will work also without PMMA buffer layer. Let's see light emission from these devices. But it's important to note the electromodulation in the spectra of our modified device, and also the light emission here. You can see again there is no emission under the electrode, so it's a good point, and also the brightness enhancement factor is one order of magnitude, so good. To conclude, we have now an organic light emitting transistor with voltage tunable lit area and full channel illumination. We have implemented a new tool for mapping the charge distribution in organic field effect transistor by confocal photoluminescence electromodulation microscopy. And also we have a new optoelectronic gate dielectric to integrate in this kind of devices, and it is able to modify the electroluminescence of the device, so it's a good point. Thank you for the attention.
Thanks for your presentation. Just a curiosity about your talk. I mean, all these devices are new devices. As far as their commercial applications are concerned, I mean, is there any expectation about the future use of these devices? I mean, are they going to be used in, say, a couple of years, 2 years, 3 years, or any plan for this?
Absolutely, yes. We have a spin-off of the CNR ATC that is working on these devices. So they are trying to develop displays. So it's yeah, it's a good good thing.
Do they expect to have a commercial product, say, in a couple of years or 1 year? Or
yeah, I think so. I think yeah, very.
But this is a spin-off, but is there any big company behind them?
Yeah, Size Getter Group. Yeah.
Thank you.
You're welcome.
Any other question about this presentation? Okay, so the first part of this event is over. I would like to thank all the people who have attended this event here or have followed the event on the web. And the second part of the event is planned for January 12, okay, in the new year. And it will last for a longer time because we will have some presentations in the morning and other presentations in the afternoon. And it will be broadcasted on the web, so it will be possible to attend it online. So thanks again for your presence and have a good day.